All right, let's dive into a field of mathematics that is, I promise you, hiding in plain sight all around you. No, it's not calculus, it's not algebra, it's something different. It's the secret language behind pretty much everything digital. Computer science, network security, even your favorite brain teasers. It is literally governing the rules of the world we live in right now. But to really get a grip on what this is, we're not going to start with some dry formula. Of course not. We're going to start with a puzzle. And it involves a bridge and three very, very tricky trolls. Okay, so take a second and really look at this. You got three trolls, three statements, and just one simple set of rules. Knights always tell the truth, and knaves, they always lie. Now, how in the world do you even start to unravel this? The maths tools you learned for finding the area under a curve? Yeah, those are not going to help you here. You need a completely different way of thinking. And that kind of thinking, the one based on pure logic, truth, and these separate, distinct possibilities, well, it has a name, and it's the key to a whole universe of problems that all have one thing in common. They deal with individual, countable things. It's called discrete mathematics. And you know what? The core idea is actually super simple. Discrete math is all about stuff you can count. We're not talking about the smooth, unbroken flow of time or the infinite, endless numbers between 0 and 1. We're talking about distinct, separate objects, things you can point to and say, 1, 2, 3. And this distinction, it's everything. Think about it. The number of kids someone has is discrete. You can have 2 kids or 3 kids, but you can't have 2.58 kids, right? It's a set of distinct whole numbers. On the flip side, something like time or the values a function can take can be continuous. It just flows, unbroken, with infinite possibilities in between. Discrete math lives in that first world, the world of separate, countable things. So how does this help us with our trolls? Well, this is where we get to open up our discrete math toolbox. And the very first tool we're going to pull out is formal logic, the actual mathematics of true and false. You see, each of the troll's statements has to be one of two things. It's either true or it's false. There is no maybe. There's no in between. And that binary nature is our key. It lets us play a what-if game. For example, let's just assume for a second that troll 2 is a knight. What happens then? Well, if he's a knight, he must be telling the truth. So his statement, troll 1 is lying, has to be true. And if troll 1 is lying, then he has to be a knave, which means his own statement must be false. You see that? It creates this incredible chain reaction of logic. You just follow each assumption until it either works out or creates a contradiction and bam, the answer reveals itself. That's the power of formal logic. But logic is just the beginning. That was just tool number 1 from the toolbox. Let's take a look at a few other kinds of problems that need this same way of thinking about separate, countable things. Let's try another one. This time, it's not about true or false. It's about counting and finding patterns. We're just looking at a sequence of numbers, but they're growing in a really predictable way. This is the domain of something called combinatorics, which is really just a fancy word for the math of counting. And what's so cool about these counting problems is that they often hide these absolutely beautiful, elegant patterns. Take Pascal's triangle right here. The rule to build it is so simple. Each number is just the sum of the two numbers directly above it. That's it. But from that one simple rule, this triangle gives us the answers to all sorts of incredibly complex questions about probability and combinations. It's a perfect example of simple, discrete rules creating mind-blowing complexity. Okay, here's a question that feels a little more down to earth. How many different license plates can you make? Again, it's a counting problem, but with so many possibilities, you're not going to sit there and list every single one, are you? So how do you figure it out? Well, it's actually way easier than it looks. You just break the big problem down into a series of small, simple choices. This is called the multiplicative principle. For that first letter, you've got 26 choices, A through Z. For the second letter, you've got another 26 choices. Same for the third. Then you move to the numbers. You've 10 choices for the first digit, 0 through 9. 10 for the second, 10 for the third. Then all you do is multiply those choices together. Simple, powerful, and totally discrete. And for our last one, let's switch gears completely. This isn't about logic or even counting in the same way. This is all about structure, connections, relationships. It's a classic problem from a whole other field called graph theory, which is all about studying networks of dots and lines. So trolls, license plates, towns, it's all interesting. But why does any of this really matter? Well, here's the kicker. These puzzles, they're not just fun brain teasers. They are miniature versions of the exact massive problems that engineers and computer scientists are solving every single day to build our digital world. Seriously, that logic puzzle with the trolls, that's the same true or false, yes or no logic that powers every single computer chip. The town and road puzzle, that's graph theory, and it's literally how your GPS finds the fastest route to get you home. Even the internet security that protects your credit card information online, yep, that's built on the discrete math of prime numbers. It is truly the invisible scaffolding holding up our entire digital lives. So, in the end, discrete math isn't just a random collection of puzzle-solving tricks. It's so much more than that. It's the fundamental language, it's the grammar we use to describe any system that's made of separate parts, whether that system is a supercomputer, a social network, or, yeah, even 3 trolls on a bridge. So here's something to think about. The next time you see a complex network, or a piece of code, or even just a tricky little puzzle, try to look for the hidden rules. Look for the countable parts, for the logic holding it all together. Because what discrete math really teaches us is that the most incredibly complex systems in our world are often built on the absolute simplest of foundations. They're just waiting for us to discover them.